In this video we're looking at what is called the modulus of x, which is written like this. Also can be called the absolute value of x, absolute value function. What this means is if I was going to have the modulus of 2, that would be 2, and the modulus of negative 2 would also be 2. If I wanted the modulus of negative a half, that would be a half. Or the modulus of minus 0.2 would be 0.2. The way we define this officially is that the modulus of x is the number x itself if x is greater than or equal to 0, that is if x is positive or 0, and it is negative x if x is less than 0. So in this case x is less than 0, so the modulus is negative x. Because x is already negative, the output is positive. A modulus is always positive. So it's just going to be the absolute value of the number, the positive bit of it. So you disregard the sign and it's going to be positive each time. So we're going to look at the graph of this. So here you've got the graph of y equals x. But what if I wanted the graph of y equals the modulus of x? Now because y is the modulus of x that we're interested in, y equals the modulus of x, whatever value of x we have, this value is always going to be positive. So if we have x equal to negative 1, the modulus of x would be the modulus of negative 1, and the modulus of negative 1 is 1. Okay, so we have when x is negative 1, y is 1, which is here. Likewise, when x is negative 2, y will be 2. We end up with a graph that looks like this. The reason we don't change this is because all these values for y are already positive. If we look at this in a more formal way, we have our graph here, and in this one you can see that your y value at every point here is positive because it's the modulus of x. Now from what we were looking at a previous lesson about whether this is a many-to-one or a one-to-one mapping, well, let's look at this. If y was 1, if I draw my line across at y being 1, you can see that x could be negative 1 or it could be 1, therefore it's not a one-to-one mapping. In general, to transform from the graph y equals x to the graph y equals the modulus of x, you have to look at the negative part here and you're going to bring it up 90 degrees like this. Each bit goes up and you're basically reflecting it here. This is a reflection in the x-axis for all the values where y or f of x is shown to be less than 0. To the original, we've got here two possible solutions. It could be if y was 1 and if y was 4 or f of x was 4 up here somewhere, you'd likewise have two solutions because it goes upwards here. Let's look at an example of how we'd solve an equation that involves a modulus function. As you can see here, we've got the modulus of x minus 1 equals 4. Now my problem here is that this value inside the modulus sign could be either positive or negative, and I'm just interested in the modulus of it, so what values of x could it take? Well, what we're going to do is we're going to square both sides, because if it was negative and I squared it, or if it was positive and I squared it, I'd get the same answer. So it's going to give me both values of x for which this is possible. So if you expand your brackets and bring it over your 16 and factorise it and solve it, you're going to get that x equals 5 or x equals negative 3. Now the reason that there's two solutions, even though it's not a quadratic originally, and that might be a bit confusing, is because the modulus could be the positive or the negative. So let's substitute these both in and have a look. So if x was 5, you've got the modulus of 5 minus 1 equals modulus of 4, which is 4, so that's correct. And if x is negative 3, you've got the modulus of negative 3 minus 1, and that's the modulus of negative 4, which is also 4. Because if we have a remember, we're going to look at another example. Sometimes you're asked to sketch the graph and use it to solve an equation. So first of all, if we sketch the graph of f of x equals 2x minus 3. So in this case, can you see, I'm not interested in the modulus function, I'm just interested in the bit inside the modulus. So this is the graph that we want, but as we can see, some of the y values are below 0. So we'd reflect those in the x-axis here, and they'd become something like this, giving us this graph here, fx equals the modulus of 2x minus 3. Now we've got to do the hence part, solving the equation of this, modulus of 2x minus 3 equals 2. In order to do that, we need to replace f of x here with 2, and otherwise we want f of x to equal 2, which would be along here. Draw my line in, and as you can see there are two solutions. One solution is here, and one solution is here. So we've got one solution at 1/2, and one solution at 2.5. So we have x equals 1/2, or x equals 5 over 2, 2.5. And again we've got our two solutions because we've changed this from a one-to-one function to a many-to-one function. We're now going to look at an alternative technique to finding the solutions, and you can choose which of these you prefer. So if we're asked to solve this equation and then illustrate our solutions in the graph, we're going to look at the fact that 9 minus 2x squared, the bit inside the modulus, is either going to be positive or negative 1. Here, because either of these, the modulus of 1 is 1 and the modulus of negative 1 is also 1. So if we solve these to find x, we've got that 2x squared equals 8, x squared is 4, so x is plus or minus 2. On the right hand side you've got that 2x squared is 10, x squared is 5, and x is therefore plus or minus root 5. So we've done the solving bit, we now need to illustrate the solutions on a graph and find out which of these four solutions, which any of these is going to give us the correct options here. So okay, here we have the graph of f of x equals 9 minus 2x squared. So I want to make this into a modulus graph. I'm going to look at everything where y is below 0. I'm going to reflect it in the x-axis, so it's going to come upwards like this, giving me this graph here where f of x is the modulus of 9 minus 2x squared. Okay. So if I want to solve the equation of modulus of 9 minus 2x squared equals 1, I'm going to find when f of x equals 1, which is here. Oh, that's a pretty bad line. And as you can see, there are four solutions, which are the four solutions that I had previously. Here, 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 and here. So you've got minus root 5, minus 2, 2, and root 5. So actually there are 4 points on which this equation holds. And I found them here and here. For example 7, we're asked again to sketch our graph. So again, we're going to start off with f of x equals 3x plus 1. And then from that, you're going to look at the negative y values to get f of x as a modulus of 3x plus 1. So let's look at those two graphs. Okay, so as usual, we looked at the negative y values, reflect them in the x-axis, and get this graph here. So we're now interested in when it's less than or equal to 2. Well, let's look at when it equals 2 here. Now at this point you've got the line that f of x equals 2, but I'm interested in all the points where it's less than or equal to 2. So you're looking at here all these points here, nicely shaded there, where you've got that this is a third, and this is not very clear, but that's actually -1. So all the points in between here are good for you, in which case the region interested in is where x is less than a third, less than or equal to a third, but greater than or equal to -1. So what you do in this case is, again, you draw the line, you think, well, it wants to be less than or equal to 2, so all these points are less than or equal to 2, so it works for this entire region here. That is, for any value of x within this region, this inequality holds true. I suggest you go and have a look at example 8 on page 11 of the textbook to see how this can also apply to trig functions. Then have a go at the 2 questions which are on the iTunes U course and see if you can answer those.